Hello everyone, this is Pal from the Department of Electrical and Computer Engineering, University of presenting on hybrid electronic photonic integrated circuits. Typically, in photonic integrated circuits, the photonic components only play the roles of providing high-speed communication between different electronic subsystems due to their large bandwidth. Some of the challenges faced are size mismatch. This happens due to the large scalability difference between the various electronic and photonic components. High energy data rate, cascadability and fan-out issues. This happens because the electrical output of an electronic component cannot be used directly to drive the optical input of the next photonic component. So to circumvent these issues or challenges, we can use novel device architectures or take advantages of the two worlds, like maybe replace some of the electronic switches by photonic counterparts. In that sense, we are overviewing the operation of 6 transistor SRAM. During the read 0 operation, the bit line BL is discharged to the path M5 M1 as shown by the arrow, and the voltage difference of the bit line is sensed by the sense amplifier, and we can say a read operation has taken place. Similarly, during write operation, the node Q bar initially at 1 gets discharged via this path, and we can say, and the self-flipping occurs, and we can say that our write operation has taken place. So as evident, during the read and write operations, the access transistors M5 and M6 plays an extremely crucial role. So if we could replace these two access devices by some high-speed optoelectronic switches, then maybe we can achieve much improvement in the read and write operation. Such a device is called a light effect transistor. Now, as seen, a light effect transistor is a very simple structure with a nanowire placed on an insulating substrate with a drain and source contact at two ends. The working mechanism of an LET is much different, and it depends on the well-known photoconductive mechanism. Since this structure does not have a physical gate, the device speed is only limited by the carrier transit delay or lifetime, whichever is smaller, rather than the capacitive delays as in all gated FETs. The electrical switching energy of this device depends on the drain source current, the voltage applied at the two ends, and the transit delay of the carriers through the nanowire channel. Similarly, the optical gating energy depends on the photonic energy incident, the drain source current, the gain of the device, and the transit delay through the nanowire channel. This optical gating energy part will not be present in case of a FET due to its different turn-on mechanism. Advantages over conventional FET structures. Since this structure does not have a physical gate, it does not require any complex gate fabrication process. The electrical switching energy could be extremely low and as low as 1.3 into 10 to the power negative 3 attojoules per switch when the nanowire is made to operate in the ballistic regime. Even with a larger device structure, the total switching energy could be as low as 0.6 femtojoules per switch, which is better than typical FETs having switching energy in the range of 0.1 to 1 femtojoules per switch. The ion-I of ratio could be as high as 10 raised to 6, which makes this device an excellent optoelectronic switch. Since this device does not have any physical gate, neither any PN junction, so we can infer that the gate induced leakage and the junction leakage will not be present in this device. However, there will be the subthreshold leakage due to the dark current, and principally since the nanowire in the device is undoped, so the dark current could be extremely low, say a few picoamperes or so. This is a 6 transistor SRAM array, and as can be seen, the read-write delays and the corresponding energies depend on the gate and drain capacitance of the access field effect transistors. Since For the LET device, there is no gate capacitance, neither any drain capacitance. So we can say that for an hybrid array, the critical capacitances will be appreciably lower as compared to regular arrays with FET access devices. This is the hybrid 6 transistor SRAM where the access FETs has been replaced by light effect transistors and the electrical word line has been replaced by an optical waveguide which does not consume any energy, neither contributes to any capacitance. For our analytical purpose, we have considered LET of two different sizes and two different drive currents for comparison. This shows a direct comparison of two array sizes with regular SRAM, with regular 6 transistor structure and hybrid structure. It can be inferred from the two tables that with the hybrid SRAM, marked improvements can be achieved in terms of read delay energy and write delay energy. Moreover, the energy delay product or the figure of merit for the hybrid SRAM array could be more than one order of magnitude lesser as compared to the regular SRAM arrays. So we can say that hybrid SRAMs will be much energy efficient when they will be used in on-chip caches. In summary, we would like to compare the performance of hybrid SRAM with LETs of two different sizes and two different drive currents. First, we consider a smaller LET with a lesser drive current, and we found out that an average improvement of a factor of 5 and 24 can be achieved in the read delay and energy respectively, while 3 and 5 a factor of 3 and 5 can be achieved in the write delay and write energy. However, with a larger LET structure with higher drive current, an average read delay improvement of a factor of 5 more can be achieved while the other improvements remain almost the same. This is because with higher drive current of the access devices, the overall cell read current increases, which improves the read delay, while the write delay, which predominantly depends on the write circuitry current, remains almost unchanged. In fact, with increase of the drive current and device sizes, the read energy and write energy increases slightly due to the increase of the optical gating energy and the electrical switching energy per LET device. As a result or as consequence, the EDP also increases for the larger device and with larger drive current. So it can be concluded that for optimum performance of the hybrid array, it's better to use smaller LET devices with optimum or lesser drive current. For some further prospective improvements, other than replacing the access field effect transistors with LETs, there may be a chance to replace some other electronic switches in the peripheral and assist circuits with LETs. Also, there can be a chance to replace the FETs in the pre-charge circuit of the 6 transistor array by LETs, which will reduce the overall delay since the pre-charge operation is mandatory before each read and write operation. Moreover, replacing the electrical word line with optical waveguides not only minimizes the word line delay and energy consumption to almost negligible, but it also abolishes the need of any extra word line driver circuitry, which are very common in all large regular 6 transistor arrays. So in a nutshell, we can say that the hybrid array is much energy efficient with much better performance as compared to the regular 6 transistor cell and array. That's all from our part. Thank you. Have a good day.